Hi guys. So today we're going to look at a different kind of factoring. What we're going to do is we're going to look at factoring that we couldn't do without synthetic division. So to start, we're just going to show kind of how this process works. We're going to prove that a number is a zero of this function. And the way we're going to do that is we're going to use synthetic division. Now, one thing that's unique about synthetic division, whatever I get as my remainder is actually the same thing I would get if I take 1 and if I were to plug that number in for x. My remainder would be the same thing as if I plug in that value for x. So what we're looking for here is a remainder of 0. That's kind of the goal. So if I do synthetic division and I get a remainder of 0, that means the number in the box is a 0 of that function. Okay, and remember, a 0 means the same thing as an x-intercept, a solution. That's a lot of the words you guys used for that. So I put 1 in the box, and then I'm going to write my coefficients. So I have 1, I have 0x squared, I have a negative 7, and I have a 6. So I'm going to start by bringing down 1, multiply, and add, multiply, and add, multiply, and add, and I do get a remainder of 0. So since I have a remainder of 0, what I have left is this remaining polynomial here, x squared plus x minus 6. And I know that 1 is a 0, because again I got 0 as a remainder. That's my proof right there. So what I can do now, if I want to factor this completely, I can look at my remaining polynomial. Now it's an easy quadratic equation that I can factor simply. I know this factors into x plus 3 and x minus 2. And then all I need to do is consider my original 0, which is 1. And if 1 is a 0, well then we know that x minus 1 is a factor. So that is the fully factored form of that polynomial. Okay, so we're going to use this same process, but the problem is what we do if we don't have that 1 to start, if we have to come up with the numbers. So before we do that, I just want to talk about a couple number sets, because you'll hear these words throughout the year and throughout next year. I just want to make sure you understand the differences between them. So there's a couple different types of number sets. They have these fancy little scripts on them, but what they stand for, N is the set of natural numbers. Okay, N is the set of natural numbers. Natural numbers are, the things that occur naturally. When you think about counting numbers, if you see a certain number of things. So this is like 1, 2, 5, 100. Okay, those are all natural numbers. What it does not include are decimals or negative numbers. Okay, Z, that is the set of integers. Okay, integers. Integers include all the natural numbers. It also includes negative numbers and 0. So integers would be like a negative 3, negative 7, 0, 1, 1000. Any of those are all integers. Okay. Q is the set of all rational numbers. And that's kind of the new word we're going to talk about some today that you'll hear. Okay, rational numbers. Now you've heard this before potentially. A rational number is any number that can be written as one number over another. Okay, so all of your whole numbers, positive and negative, 1, 7, 0, negative 14, because those can all be written as that number over 1. This also includes fractions now, so like 1/2, negative 3/7, those are rational numbers. This also includes decimals as long as they can be written as a fraction. So like 0.25, because that's the same thing as 1 over 4. 0.98, that could be 98 over 100. So there's lots of different options for rational numbers. What's important here is to realize what is not a rational number. So examples of things that are not rational numbers would be something like the square root of 2, because there's no perfect fraction to represent the same value as the square root of 2. Another thing that's not a rational number would be pi, or e. Because while there's fractions that can come close to estimating it, there isn't one fraction that's exactly the same thing. Then the last set is that fancy R, which you're used to writing maybe for domain and range. That's the set of all real numbers. And that's just everything, as long as it's not imaginary. Okay, all real numbers. That includes rational numbers, it includes pi, it includes the square root of 2. It's everything from negative infinity to infinity. Okay, now the reason we bring those up, just in case you hear them later on, but also because we're about to talk about, oh, here's a little visual of what we just talked about there. So the natural numbers are on the most inside part, then it's your integers, then it's your rational numbers, and then it's all of your real numbers. So the largest number set is your real numbers. Okay, so the reason we talk about rational numbers is because now we're going to look at something called the rational zero theorem. Okay, the rational zero theorem is what we use to figure out what numbers we're going to plug in for synthetic division. Okay, so the rational zero theorem tells us the possible rational zeros of a polynomial. Now, notice that it says rational. I could have something like the square root of 2 be a 0, but that's not going to come up from here. This is going to give me whole numbers and fractions. Okay, so what we do is we look at p over q. P is the factors of the constant term, which is usually the last term. Okay, it's the number without any x's. Q is the factors of the leading coefficient, which is usually the first number, which is the number in front of the largest exponent. So if I look at this example here, I want to find all of the possible rational zeros. I'm going to find all of my p values first. So p is the factors of the constant term, which in this case is -8. So I think about all the factors of -8. Well, those could be 1, 2, 4, or 8. And any of those could be positive or negative, because as long as one of them is positive and one of them is negative, I'm going to get a -8. So those are all plus or minus. Okay, then we look at Q. Q is the factors of the leading coefficient, which in this case is the 4. So the factors of 4 are plus or minus 1, plus and minus 2, and plus and minus 4. Then the last thing I do is I find all the possible solutions for P divided by Q. Okay, so the easiest thing to do is just start with the first one and write that over every number. Okay, so my P over Q values, I have 1 over 1, 1 over 2, 1 over 4. Then I have 2 over 1. Then I have plus or minus 2 over 2, but that's 1, which we already have. And then 2 over 4, that's 1/2. I already have that as well. So I don't have to write them twice. Then I have plus or minus 4 over 1. 4 over 2 I already have. 4 over 4 I already have. And then plus or minus 8 over 1. 8 over 2 is 4, which I already have, and 8 over 4 is 2, which I already have. So those are all the possible rational zeros. So these are the numbers I would test with the synthetic division in order to be able to factor. Okay, so that's what we're going to do to factor something like this. Now, if we look at this, we can try grouping. It's not going to work. So we're going to use the synthetic division process. So the first thing I'm going to do is I'm going to come up with my possible rational zeros. So I'm going to come up with my p and my q values. So my possible p values, positive or negative, 1, 2, 3, and 6. Possible q's are 1 and 2. So the possible p over q values would be 1, 1/2, 2, 3, 3/2, 6, and that's it. And those are all positive or negative. Alright, so what we do is we pick one of these numbers to start off with, and that's going to go in the box in synthetic division. So let's start with a positive 1. I'm going to write my coefficients. Here's 2, 1, -13, and 6. I'm going to bring down 2. 2 times 1 is 2, and I add 3, -10, and I do not get 0 as a remainder. Since I did not get 0 as a remainder, then that tells me that this is not a solution for my polynomial, which means that 1 is not a 0, so x minus 1 is not a factor. So now I have to try again. So I'm going to go ahead and try again, and I'm going to use 2 this time. Okay, so I'm going to plug in my coefficients. And that gives me 4, that gives me 10, -3, -6, and I get a remainder of 0. Once I get a remainder of 0, I know that 2 is a 0, and in this case I'm looking to factor this. So I know that x minus 2 is a factor. So I'm going to look at the remaining polynomial. I've got 2x squared plus 5x minus 3. I can factor this. This is going to factor into 2x minus 1 and x plus 3. And then my remaining factor was from that synthetic division, which would be x minus 2. So that is my fully factored polynomial. All right, there's one last thing we're going to look at, and that is just going to be finding all of my zeros, okay, all of the real zeros, which means I could have some irrational zeros here. But we're going to start this off the same way, okay? I'm going to start by finding the possible zeros, the p over q values. So in this case, everything's going to be divided by 1, so it's going to be plus or minus 1, 2, 3, 4, 6, and 12. And then just to speed this along, I'm going to go ahead and start with 3 because I think it's going to work. So here's 1, negative 5, 2, and 12. And I'll do my synthetic division. And I'm going to add instead of multiply. A little bit ahead of myself. And then I get 0 as a remainder. So now I look at the remaining function. My goal here was not to factor, my goal was to find the zeros. The reason for that, if you look at this remaining polynomial, x squared minus 2x minus 4, I can't factor that. There's no numbers that multiply negative 4 and add to negative 2. But I don't need a factor, I'm trying to find the zeros. Well, I already know one of those zeros, it's 3, because I got 0 as a remainder. So what I need to do now is find the zeros for the remaining function. Now the zeros the way I find the zeros is a couple different methods. If you have a calculator, you can graph it to find that decimal, but we don't want the decimal, we want the exact value here. So the two best methods would be either the quadratic formula or completing the square. And I'm going to go ahead and use quadratic formula because I think it's a little bit faster, or a little bit easier, I should say. I think completing the square is actually faster. And that's negative b, a little bit off today, sorry. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So then I plug in those numbers. That gives me 2 plus or minus square root of negative 2 squared minus 4 times 1 times negative 4 all over 2 times 1. So I can simplify this now. 2 plus or minus the square root of 4 plus 16, which I'm going to go ahead and write as the square root of 20, all over 2. Square root of 20 simplifies to 2 root 5. And since all of those numbers have a 2, I can divide that out, and I get 1 plus or minus the square root of 5. So there are 3 zeros here. One of them is 3, one is 1 plus the square root of 5, and then my last 0 is 1 minus the square root of 5. Now you won't always need to use the quadratic formula. That's just if you're trying to find zeros and you can't factor. If you can factor, that's always faster, and I would do that first. But that's a process for factoring using synthetic division.